Hello everyone and welcome. My name is Rodrigo and today we will be solving another LeetCode problem in APL. Today we will tackle problem 1791, find center of star graph. Now before we jump right into it, I've been getting some comments telling me that I sound like the volume is too low. So I try to increase it a little bit for this video. And just let me know if it's better now or if it's still not enough or if I'm too loud right now. So yeah, the problem is fairly simple. We will be getting the input to our function will be a representation of something like this. This is a graph, and they call this a star graph because there's a node in the center and all other nodes connect to it, and we just need to compute the center. Now the way we get the edges, so the edges are these little lines connecting the nodes, the dots. An edge is just a pair of numbers, and the two numbers represent the two nodes in that are connected by that specific edge. So for example, this star graph right here, this is represented by this list of edges. Notice that the 1, 2 corresponds to this edge right here, the 2, 3 corresponds to this edge right here, and the 4, 2 corresponds to this edge. And our task is to determine from the list of edges, we need to determine what the center of the graph is. And that's essentially just taking a look at the list of edges and figuring out what number is repeated, because a star graph always looks like this. Are there any more? No, there's no more figures, but for example over here, the center of the graph is 1 because 1 is the only element that shows up in every single edge, and also it's the only number that's repeated. And so we can leverage that in our, let's see if I can get a blank screen for you. And because the center of the graph is the only number that is repeated in any of the edges, we can just take a look at the first two edges and see what's the number that shows up twice. And so let's see, let me define the edges. So the edges are, for this particular graph, are, and let's assume that they are a nested vector. So let's say that they look like this, 1, 4. So these are the edges. How can we solve this? Well, it's simple. We only need to look at the first two edges, so we can do a two-take, and then we can where's the symbol? We can intersect the two edges with a reduction. And then we can pick the only element that's in there to retrieve the center. Now this is, well, that's it. This is the only thing we need to do. And the good thing of using the two-take is that so we use the input was a nested array here, but because this is APL, maybe the input would be something like this. So a matrix where the first column is one set of nodes and the second column is the connected set of nodes. If our input also looks like this, then the solution we had before, which is just this, will still work. So I just copied it, and I will paste it in front of the input, and it didn't work. So what did I do wrong? I'm doing something wrong. So when we this takes 2 rows. Oh right, of course it doesn't work. Now I need to do the intersection on the whole column. So sorry, on the whole row. So of course that wouldn't work. Okay, so if the input is a matrix instead of a nested vector, then we need to do something about it. What can we do? I mean, I guess we can split. Now what if I split again? Yeah, it wouldn't. Yeah. Okay, so never mind. I was so confident that that solution will also work for verbatim for matrices, but it doesn't. So our solution, just to take a look at it again, was the first element. So it was us unpacking the result of the intersection of the first two edges. And now we don't want edges in there, we want the argument. So the solution is just this. And for the other example, let's go up, it's in here. For the other example, it's just 1, 2, 2, 3, 4, 2. There you have it. And we can also create a tacit solution. So a tacit solution, and that's just going to be, so let's take a look at the solution to build it tacitly. So this is the thing that happens first, and then this thing, this and this, they all just happen in sequence. So this is just one thing after the other, and in order to do that we can do something like the peak after the intersection after the two take. And if we call it on the edges, there you go. Now this makes it abundantly clear that we are doing one thing after the other. You can reformat this in many different ways. For example, let's try to make it prettier. Let's do a peak atop this intersection, and then it would take, let's see, did I get this wrong? I don't think so. Okay, so let's see what this looks like, because that makes it clearer how the tacit solution is working. So by having the peak outside of this parenthesized expression, I'm telling APL that this comes after, so this happens after the function on the right, because this is just two functions, and so it's an atop, and so the second one, or the one on the left, happens after the first one. And then the first one is just whatever's happening in here. Can I select these columns? Yes. So the first one is whatever happens in here. And now this is 1, 2, 3, 4 elements. So the first three elements are seen as a fork, and then this reduction right here is also happening on top of the result of this. So this reduction happens after this thing is ran. Now this thing right here, this is just a to take of the right argument. So that's it. Yeah, tacit can be really elegant, but it can become confusing if the functions become too long. So yeah. Well, I think this is it. Let's take this opportunity to show you something else. So and this is a solution that is not very efficient, but does work for matrices and nested vectors. So if we have these edges, again, we just need to find out the only number that is showing up repeatedly. So what we can do is we can flatten everything, because we don't really care about the structure of the input. And then we can use, I think this is an 18 feature. So if you're using APL, Dialog APL 17.1 or a previous version, it won't work. But in 18.0 we get this monadic not equals, which is a unique sieve. So this gives me the positions of unique numbers. So the zeros correspond to numbers that showed up repeated. So if I negate that, now I know these numbers are repeated. And so what I can do is I can compress the edges with that information. Right, it needs to be flattened, sorry about that. Yeah, so then I can compress the information of the nodes, and then I just pick one of them, because they're all going to be the same. And if I change edges to be the second example, it was something like 1, 2, I think, and then 4, 2, and 2, 3, or something like that. It works the same. So this is a solution that also works if the input is a matrix. So if I mix this here, it still works, and now the input was a matrix. Yeah, so these are two example solutions. The first one was more efficient. This one was just to show you how the unique mask over here works. And if you have any other alternatives, or if you have questions, feel free to drop them in the comments. And yeah, follow the GitHub link if you want to add alternative suggestions to the GitHub repo. Well, I'll see you in the next one then. Bye.